Whenever's good with you.
All right. I did my project on the Seriatel churn data. All right. Oh, hold on. Let me move these windows over here. So the objective of this set was to find a correlation to see if a customer was about to basically leave to another provider. The data we used in this, or I used in this, for this project was the data that was provided by Seriatel that just gave basic information on customer on their accounts, like, the type of plans they have, how often do they call, the amount, that they call, like, minutes wise, and the amount of customer service calls. Some interesting things that I discovered when I was looking at this was basically, customers, it was kind of, suspected, but customers tend to leave at a lesser rate if they have a plan like this international plan. The customers, are kind of 50-50. But if you look at the people that don't have a plan, like it's a lot more, leave. Sorry. Over here, we have customers that have over 4 um, customer service calls. In this area right here, you can see that they tend to leave if they have to call more often, or if they get charged more for their, I want to say it's their daily charge, which I'm assuming it's, night, evening, and day, All right. So for the most relevant features, I was able to get, an idea of which were going to be the most important with one of my earlier models. Customer service calls, as expected, was the most important. And another thing that I noticed was that 15% of the total, I want to say it was like 33,000, or sorry, 3,333. Uh, Out of that, 15%, left. So we really didn't have that much, like balanced data to work with. All right. So for the base model, I basically just made a function and I was able to run, I want to say like 6 different models with that function to give me an idea of which ones were going to be most effective. The 2 winning models were Random Forest and XGBoost. I know it doesn't look like it here, but yeah, it was a lot better than some of the other ones. The first thing I did for my final model was use Tomek links, which basically like allowed me to cluster the data in a way that, the models were able to look at it and understand it better, so they didn't like bleed into each other, if that makes sense. Um, I ran it twice. After the second time, it really didn't get rid of any, data points. It got rid of like 6, I want to say, compared to the first time that it got rid of like 89 data points. And then I used Smote to generate new values in the minority cluster. This basically just, allowed my data set to have, 50% no's and 50% yeses, as in people who left and stayed. Also, for my final model, I was mostly interested in increasing the recall score because even though, it was going to give me more false positives, that wouldn't necessarily be a bad thing for my, end goal. All right. So after, I fit the model and grid search it to find the most optimal features, it gave me these, I don't know if you guys can see it, but it gave me these important features for XGBoost and my Random Forest model. Both, as expected, customer service was the most important for, both. And then the second biggest impact was probably the, like total charge and total minutes, throughout the day for everything else. And the final results compared to my base model, we were able to, or I was able to correct the class imbalance issue and increase the recall score, especially with the XGBoost. I got it from 0.5 to 0.85, which is pretty good. For Random Forest, it was overfit the very first vanilla model, I managed to fix the overfitting a little bit, and the testing recall stayed somewhat the same. Conclusions, basically, more plans, Seriatel should offer more plans like international calling. If a customer calls customer service more than 3 times, Seriatel should give them like special attention or better deals, to prevent them from leaving. If they suspect a customer might be leaving soon, they should offer, like a special promotional deal so they, are more inclined to stay. Uh, Next steps would be I would like to, explore the relationship between customer churn and the time of day usage, because I believe that would give us the ability to offer more like personalized plans to certain customers. And also, if we had more data on people living, that would increase the accuracy of the model. And thank you to Yisha and my cohort mates for the guidance and towards science, mostly towards science. Medium Stack Overflow, StatQuest, pretty cool, but towards science, and especially this link on Beginner's Guide to XGBoost did wonders for me. And that's pretty much it.
Awesome. Thanks, Edward. I'm thinking of not doing questions for this round of presentations. Any questions that you have for each other, just put them in the chat, and I think y'all can just communicate that way in the interest of time. All right, thanks, Edward. Next up, we have Kevin.
Yep. Hey, everyone. Happy New Year.
Happy New Year.
Okay, let me share my screen. Here it is. Okay, can everyone see my slides?
Yep, you're good.
Okay.
Yes.
So for my project, I put together a music genre classification model. I came up with the scenario around that. Shazam is an app that we've all probably heard of that is able to identify a song by a short audio clip of that song. I thought it would be interesting if Shazam could also tell you the genre of a song that it wasn't able to identify the title of. So that was sort of the inspiration behind my model. The secondary goal was to see if we could learn anything on a quantitative level about the differences between musical genres based on sort of the information that you can derive from the waveform of a song, which is the raw data of the audio file of a song. So the data I looked at came from Spotify, and there was actually 10 different features in there that describe each and every track that I looked at. Most of them are again derived from the audio waveform of the track. So things like acousticness, loudness, instrumentalness, valence, which is like the mood of the track, happy or sad. Speechiness, is there spoken word in the audio file, or is it just instruments and singing, that sort of thing. There's a lot of detail here that I won't run everyone through now, but ultimately I collected a sample size of about 2,000 tracks, and I categorized them into these 10 different genre categories. I'm sure we've heard of all of these genres. It was interesting down the road to look at how good my model was at predicting certain genres versus others. This wasn't a binary classification. It was obviously a tenfold classification. So the model was definitely much better at identifying certain types of music than others. And as you could guess, think certain genres here might sound somewhat similar, and we can get into that later. As far as methodology, I again came up with this group of 10 genre categories, and I ended up training pretty much every algorithm we learned in module 3 to just get a sense for which algorithm would naturally work the best with this kind of classification problem. After that, I picked the top 2 or 3 performing algorithms and did some grid search and some other analysis to sort of fine tune those parameters. And then the resulting models I wound up with were a random forest and a gradient boosted trees model. Those were the two best performing models that I came up with. And as for results, the main question I wanted to know is, can you use information from the audio file of a song to predict what the genre of that song is? And the short answer that I found is yes. All of the algorithms that I attempted to build a model off of were at least 50% accurate overall across all 10 genre predictions, which is a huge step up from just random chance guessing, which would be 10%, at best. The best algorithms that I wound up with at the end of it all, I managed to get up to 65, 66% accuracy. So pretty sizable distance that I was able to build there between sort of the lowest performing baseline accuracy levels and what certain models were able to do after I spent some time tweaking and tuning them. And then again, as I mentioned, one of the most important takeaways from all this is that, the models are naturally sort of better suited to predict certain genres versus others. So not every prediction is created equally. Let's see, with the gradient boosted trees, my overall model accuracy was 66%. And we call this plot a confusion matrix here. So you can read diagonally downwards from left to right and count the raw number of all the correct classifications that the model was able to do. And you can see that diagonal line going through the middle has the biggest numbers on the chart by far, which just sort of anecdotally you can take away to mean it was able to correctly classify most of the tracks that we put into the model. As far as taking that a step more detailed, how good is the model at actually identifying each genre? Well, it turns out it was best at classifying classical tracks and metal tracks, which are sort of like two completely opposite ends of the musical spectrum, as everyone might be able to tell. So that's not a super surprising takeaway. Similarly, it was worse at classifying blues, which it frequently thought might be either hip hop, country, or jazz. And this wasn't surprising to me either, because blues and hip hop and country and jazz are all sort of related as genres. I don't know the exact orders of when each of these genres was officially established, but they grew out of each other and were influenced by each other. So there's a lot of overlap there. And that just makes this sort of an expected result for me. As far as the quality of the predictions coming out of the model, again, classical was a really strong one for our models. It's really easy to predict. And when you do get a classical prediction out of the model, it's going to be correct 94% of the time. So almost always. On the flip side, if you get a blues prediction coming out of one of the models, it's actually more likely to be jazz or hip hop. And there's a similar situation with predictions of disco for a given track. The model confuses disco and hip hop. So there's a strong chance if the model's telling you a song is disco, it might actually be hip hop. The results were actually very similar for the random forest model. So I won't go through those in detail, but the percentages were sort of in pace with what came out across the board for the gradient boosted trees model as well. Ultimately, this leads me to a couple recommendations. First of all, yes, we can use audio wave data to predict a genre. But again, the genre predictions only work well on certain genres. They don't work well on all genres. So one next step that I think is important is to, first of all, make sure we have more unique examples of the harder to predict genres like blues and disco included in our data set moving forward, and that's going to take some research. Additionally, perhaps changing the grouping of target genres that we're trying to predict would help improve the overall accuracy of the model. As far as the most important features, again, we saw similar results between the two models here, both in terms of the top 6 features that were the most important and the bottom 4 least important features. Now, within those top 6 important features, different features were sort of more or less important between the two models, but as a group, the 6 most important features were the same across the board. And again, this confirms for us that an audio waveform can in fact be a predictor for genre. However, one of the most important 6 features included in there is popularity, which has nothing to do with the audio data that you could derive from a track. That is completely unrelated. And so it is important to note that the addition of other forms of metadata, such as popularity, could certainly help to improve the accuracy of a classification model performing this kind of task. As far as future work, it would be really valuable to do a more in-depth genre mapping exercise. Again, to make sure we have the very right set of target genres we're trying to predict, and also that for those harder to predict genres, we have enough unique examples of music that falls into those genres that our model is able to make those predictions. I also think as far as expanding the project and moving into phase 2, it would be a good idea to build out a pipeline where we could test individual Spotify tracks as inputs for prediction in order to further refine the accuracy of the model sort of on a piecemeal basis and sanity check what's going on. So thank you very much. And that's my presentation.
Thanks so much, Kevin. All right, let's see who's next. Next we have Christina.
Hey. I'm just sharing my screen.
Awesome.
All right. So I did the Chicago car crash data. And basically what I looked for through it is primary causes of car crashes in the Chicago area, main types of these car crashes, and what drivers can do to prevent the crashes. What I focused on was make a model to predict whether the main cause of the car crash was a driver's failure to yield. The data used was Chicago traffic crashes, and there were 2 separate data frames, one that focused on the data about the crash, and then focused on another one that focused on the data of the people. And both of those can be found right here. Overview of it, the time frame, the data collection started in March of 2013, and it is ongoing. The last data points that I have are from December 2020. After cleaning, we had about 442,000 rows. So it was a large data frame. So I looked at driver's actions and seen how it related to the car crash. And the biggest one that I saw that wasn't unknown was failure to yield, which is why I decided to focus on it. If we look at it, the class unbalanced is a little high. It is a little more than 3 to 1. Now, if we look at failure to yield versus the crash type, we can see that the most common crash types for this one was angle, turning, and side swipe, same direction. A surprisingly high one, which I would like to look more into and how this is considered failure to yield, is parked motor vehicle. It just seems like a strange one to be in this category. So another one, when we look at failure to yield, another big one was driver vision. And we can see that most of the time, if you're failing to yield, it's not because you didn't see something coming. That most of the time it's just not paying attention or not yielding. The time of crash, it makes sense. Most of the crashes occur during after work rush hour, which tends to be about 3 to 5 p.m., which makes sense because that's probably when there's more cars on the road. And to a lesser extent, before work rush hour, about 7 to 8 a.m. So my baseline model for this was the dummy classifier, which makes predictions using simple rules. I use stratified, which predicts based on class. So it's quick, simple, and it's a quick, simple distribution. And since we have a lot of rows, doing anything like with that deals with distance, like KNN, just takes hours to run. So my final model, which I used, was the decision tree with a max depth of 5 to avoid overfitting. And it much better than the baseline model, but we still can work on the precision score or the F1 score. And here we can see the confusion matrix, which looks pretty great. And the time for a model like this is for a data set this large was actually pretty good. So this is the decision tree. It's hard to see on this, but basically you can see that much like a flow chart, it just splits things until you have it. So my recommendations using this model is in driver's education, really focus on the importance of yielding, especially when you're turning, changing lanes to avoid those types of collisions. During rush hour, when everyone is in a rush to get home or get to work. For filling out the crash report, if we remember back to the first, to a little bit before, we saw that a lot of them have like unknowns, and this is something that came up again and again in the data sets. So, or had multiple things meaning the same thing. For example, a side swipe, and so I think having language to help avoid multiple values meaning the same thing, and so that we can get less unknowns in this, and we can get a better sense of what's actually happening. So for the future works, I would like to examine how other actions can affect the model. There's a third linked data frame that covers the cars involved, which I did not get into, but in the future, it might be a good thing to see. Maybe trucks or vans are more likely to be in this and cause these crashes. And to streamline the data, research the differences in the crashes and causes, maybe binning a couple of them together, putting them together, and seeing what things like yielding to a parked vehicle actually means. And then cutting down the data, maybe combining, see if we can combine some rows based on the research that we find about the crashes and the causes. And then also if we had a more powerful machine, run other models that just take longer with the CPU available at the time. Thank you.
Awesome. Thanks so much, Christina. All right, next up we have Marvin.
Oh, wow. I guess I came just in time. Hey, what's going on, everybody? Hold on for a second so I can share my screen. 1 second here. All right, got that. Uh, 1 second. All right, can you guys see the screen? All right, cool. Let me just move this out of the way. Okay, so this is analyzing Terry stop data to predict frisk events. There should be an S on there. So we'll get into the background and context, and then also do some EDA, pre-model insights and visualizations, get into the modeling, and then recommendations and conclusions. So just for background on this, the client that I chose was the Center for Constitutional Rights. The Center for Constitutional Rights actually filed and won a case in New York City back in 2013, where the New York City Police Department was found liable for a pattern and practice of racial profiling when it came to stop and frisk. And so the Terry stop data is actually taken from a case. I didn't put that information here, but taken from a case, Terry versus Ohio, many years ago, and where there was ruled that a Terry stop was actually essentially okay to do. So stop and frisk was okay to do based on having some idea or thought that an individual might be suspect. And so the interesting thing about the Center for Constitutional Rights is that they actually run a case where the New York City Police Department was found liable for actually stopping and frisking people of color. So the goal really for this business case is to analyze for stop and frisk bias in the Terry stop data and identify whether a frisk event can be predicted to support the ongoing efforts to combat injustice. A little bit about the data. So Terry stops came from data.gov. It's publicly available, no use of an API. Around greater than 45,000 entries from around 2015 to 2020. Essentially, one entry equals one stop. Also, some interesting things about the data. Greater than 13,000 entries for call type, where no info on the call type was provided. And then there was some class imbalance with respect to arrest flag, but also with respect to frisk flag, around 1 to 3.4. 1 meaning that someone was frisked, 3.4 meaning that someone wasn't frisked. So getting into some of the EDA, I did go ahead and create some features. Initially, the data set, just had the timestamps, the date stamps and things like that. So I created features for time of day. So for the morning, evening, overnight, and then the afternoon. I also created features for the quarter where the stop took place, and then also the reported year. And so you can see there all of the variables. And because the idea was to predict based on frisk, and also to do my best to not make this biased, the goal was to also remove information related to the officer's race, related to the officer's gender, the officer's year of birth. I did keep subject perceived race, but I did remove subject perceived gender because the majority of the entries in the data set were male. So I didn't want that to impact. So you can see the class imbalance, of the variable frisk flag there. So a little bit of EDA insights. So number one, 911 calls in the evening and overnight were pretty significant. If you can see from the left, the grid there, heat grid, but then also 911 calls in the evening and overnight, but then also for individuals in ages 26 to 35 in the evening and overnight as well. So yeah, just essentially 911 calls, 26 to 35 in the evening and overnight has some significance in this data set. My final model was a random forest model, accuracy score of 0.53, a recall score of 0.70. I was eventually looking for F1 and recall scores. The the baseline model had a higher accuracy score, but also lower for all the other scores. The feature that time and time again was the most important was call type not reported. So I was actually glad that I kept that feature, or that what would you call it? I was actually happy to keep that entry not reported and not to call it something else, because I think it does speak to the significance of data being input by police officers. Another thing related to the modeling, the logistic regression, I ended up doing some smoke data, and I did, ran a for loop to look at how more of the data being exposed to, or less of the data being exposed to smoke data, how that would impact the scoring. So what I did see is that as the test size increased, meaning that more of the data would not be smoted, I did see that recall had the most sensitivity to that process. And generally, as true positives went up, false positives went up too. So this is just on the left, it just shows the initial model that I did for the dummy variables, dummy classifiers, excuse me. And you can see that the accuracy score is 0.64, but all of the other scores are pretty low. The one that I wasn't able to improve the most was the precision score. Slight hyperparameter tuning didn't improve the model significantly, and the model seemed optimized for accuracy. But the reason why I thought about random forest and using that as a final model is one, because it did help me to understand feature importance, but then also because it takes this random subset of the variables. I also wanted to see what that, how that would impact the model as well. And so I went ahead and went with random forest for that purpose as well, because of the random subset. And then to close, analysis shows risk events are not predictable given the data construction at the moment. I would really look for data sets that were more skewed to non-emergency stops. And then I would also do some undersampling using smoked. And that's pretty much it.
Great, thanks so much, Marv. Let's see, next we have Henry.
Okay, let me share my screen. Let's see. All right, it's looking okay?
Yep.
All right, good. So I did the car crash data as well. And for data overview. So the problem I was decided to look at was it's a look at what sort of accidents led to serious accidents, serious injuries or fatalities. I used the data from Chicago. So Chicago, I think the data was mostly from 2017 to present, the data I used. And I merged it again with the data set of people. So, and then I filtered out only the drivers, because I also had passenger data in the people involved in the car crashes. So the total data set of the accident was about 460,000 entries. I pared that down to 70,000 for manageability, and then ultimately to about 56,000 after removing outliers, such as drivers who were 3 years old. The final columns, also there were lots of columns, things like the direction of the road, and I eliminated all the columns I didn't think were relevant to my purposes, and my final columns included the speed limit posted, the weather conditions, lighting conditions, roadway conditions, the number of vehicles involved. Actually, it was the number of units, which could include pedestrians or bicycles. Accident times, such as we had the hour, the day of the week, and the month, and the age and the sex of the driver. I always use just one driver for per crash. My target was a serious accident. So every accident was graded as one of 6 different in severity. I combined fatal and incapacitating injuries into a single column. I called serious accidents. Sometimes you'll see in my charts, I often call it severe accident, same thing. It was an imbalanced data set with 1.85% of accidents in my data set being considered serious. So I split that data into training and testing data, and I used Smoke to balance the training data, so it would have a better time of predicting serious accidents. I also used the Get Dummies feature for the categorical data. So for exploratory data analysis, the age of the drivers in all sorts of accidents, you can see that people in their 20s have the most accidents, and then it goes down gradually over the years. I found this was actually a very similar pattern in serious accidents as well, but I don't have that chart here. For the sex of the drivers, serious versus not serious accidents, men have more accidents than women, and the serious accidents or here have severe are more likely to be male and less likely to be female for the drivers. So my modeling, for initial modeling, I ran through all, basically, I think there were 11 models. Well, that's what I used, 11 models that we went over in our class. These are default parameters. I decided to focus on recall instead of accuracy or another metric because I want to prioritize the serious accidents, just like you'd want to, for like predict cancer, you didn't care as much about false positives. I didn't care as much about false positives for these because I wanted, I had a public safety component in my modeling, in my purpose. So as you know, so recall has true positives divided by true positives plus false negatives. False positives aren't anywhere to be seen in that metric. And also I look to avoid overfitting the training data, of course. So these are the initial 11 models I ran. I chose the ones with the highest recall, which were naive Bayes, logistics regression, and random forest. I ended up focusing, I tried with logistic regression, but I couldn't get my numbers to move much at all. So I ended up focusing on naive Bayes and random forest. So for naive Bayes, I ran several models and I used grid search. The variable, the parameter bar smoothing 0.1 had my best model. But still, I realized like I had far too many false positives to make it a useful model. As you can see, I have 8,809 accidents that were predicted to be serious that were actually not serious. And my scores overall just weren't that good for the other metrics as well. Only a 3.9% F1 score. For my random forest, again, I ran several models and used grid search. My model with the parameters with a max depth of 2, 10 maximum features, and 5 trees. I had the best recall with the least overfitting, but still the scores were not that great and still had an overfitting problem with a large discrepancy between the train and the test data. Still, I thought it was interesting to see the important features of my decision tree model, and the darkness was the most important feature. Thursdays seemed to have the most the most impact on the model as well, and the number of units. For again, the number of units for serious versus not serious accidents, except for 2 where there were less percentage of severe accidents. Every other, either one where I guess is a person drives into a tree, or larger accidents, more units involved seem to be more likely to have high percentages of serious accidents. So possible additional steps, you know, I said I wasn't too happy with my scores. I think I emphasized recall too much. So I would run the models again with other metrics, looking at other metrics. I'd also had a problem with the overfitting. So I'd say reran the models. I would play around with the parameters and try to reduce my overfitting problem. And also, if I could, with a more powerful computer, I would try to use the entire data set and see how that would affect my results. And that's all. Thank you very much.
Awesome. Thanks, Henry. Next
You're
up,
welcome.
we've got Meredith.
Hello. All right, let me share my screen. All right, so I worked on the water pump project. So the purpose of this project was to create a model that can predict the functionality of water pumps using data from Tarifa and the Tanzania Ministry of Water. So I approached this project by creating actually 2 different models. I had one with binary classifications and one with ternary classifications. So one model would predict whether a pump is functional or not functional. And then another model would predict on the 3 classes, whether it is functional, needs repair, or doesn't work at all. And then I would draw some feature importance from the final models to see what features impacted the functionality of the pumps. So the data used was provided by Tarifa and the Tanzania Ministry of Water. It was found on drivendata.org at this link. And so the original target class was ternary, with 54% of the data representing functional pumps, 38% representing non-functional pumps, and 7% representing pumps that are functional but need repair. And so I used those for my ternary model, and then for my binary model, I just combined the non-functional pumps with pumps that needed repair, because if it needed repair, it wasn't functional. So as I started my EDA, I was able to create a map to show the location of the pumps, and with red representing the non-functional pumps, green representing functional water pumps, and yellow needs repair. And you can definitely see that there are some areas where there's a lot of green, and there's some areas where there's a lot of red. So it looks like location may have an effect on the functionality of the pump. And then I went through all of the different features, but two that seemed to be significant in some ways was it's called quantity of water, a classification, and you can see that dry is really represented in non-functional. So that definitely looks like a feature that might be important. And then if we look at the construction year, we can also see that there's a definite distribution of the pumps that were made, earlier in time, having a correlation with the functionality of the pumps. So I wanted to keep that in mind as I went to my models. So for my final models, I picked the k-nearest neighbors and a decision tree. A KNN works by finding the distance between query and the examples of the data using the specified number of examples, which is like your n neighbors, your closest neighbors number, and then it predicts the classification by voting for the most frequent label in that area. And then a decision tree just basically breaks down a data set into smaller and smaller subsets, making a decision tree incrementally developed. So in my binary model, I wanted to do this one because I knew it would be cleaner and nicer than my ternary model because of the class imbalance in the ternary model. And for this one, I was able to create, the best one was the KNN, and it has a pretty even precision, recall, and accuracy F1 score. So I think it does predict pretty well, especially compared to my final decision tree model. I decided to have two, a KNN and a decision tree, as my final models, but overall KNN worked the best for the binary. And then KNN also worked the best, I decided, for the ternary model, because the KNN, I did have a large set of data. So I was able to use some of the information I learned in my binary model on my KNN to help me with my ternary model, because there was so much data, it would have taken a very long time to do a grid search with the KNN. So I used some of the parameters that I learned in the binary model and started from there on my ternary model. And you can see that the accuracy score is actually better in the decision tree model, but I felt that the other score, the recall score and the F1 score, were better in the KNN model. And this was important because of that third classification. So interpretation of the models, overall, the KNN model, the binary KNN model had the best scores. And then for the ternary model, the KNN model had higher recall in F1, while the decision tree model had higher precision and accuracy. So the KNN model was better at finding all the positive samples, a lower false negative rate, whereas the decision tree had a lower false positive rate. And however, the KNN model had the best ratio of recall and precision represented in the F1 score. And the KNN model was better at predicting pumps that were functional but needed repair, as you can see over here. And the 3.3 was the needs repair pumps, and that was the hardest one to predict because of the class imbalance. So I really focused on that. And then from my decision trees, I was able to see some feature importances, and it definitely looks like dry was important. And then also you can see that the location, longitude and latitude, were also pretty important. So in my conclusion, the K-NAN model performed the best on the binary classification. And the K-NAN ternary model had the best F1 score, the ratio between precision and recall, and predicted pumps that were functional but need repair the best. And some of the features with the most importance for the decision tree model included dry water quantity, location, and year constructed. And so for the next steps, I would further the feature analysis by maybe grouping similar features to create a smaller set of data. I also used SMOTE to address class imbalance. And I would also look into trying other methods to address class imbalance, such as undersampling. And then also looking into our new module, the PCA algorithm would also probably have helped because there was so much data. All right, and that is the end. Thank you so much.
Awesome. Thanks so much, Meredith.
Mm.
Next up, we have Sawyer.
Can you see?
Yep.
Okay. Not. I'm presenting on the telecom industry and customer retention. So the business case is, as a consultant for a telecom company, I'm analyzing why and if customers left, so they churned, and what can be done to stop them and potentially attract new customers. So the data, as other people have said, it was provided from the telecom churn data. There were 3,300 observations across 20 attributes, one of which was the target churn. And the data was pretty biased because about 2,800 of them were false, meaning the customers did not churn or the customers did stay. So moving on to the EDA, the first thing I kind of did was I smoted it, or I guess the last thing, because it was such a clear imbalance. But then looking at the data itself, the first note is that none of the data was really correlated with the target churn. You can see the table here. Nothing had close to a +1 or a -1, although International Plan had the closest. But then looking at the correlations with each other, a lot of the data was actually quite correlated. You can see the graphs here are pretty near perfect lines, and you can see these are the actual correlation coefficients. And so I dropped one of each of these just because it seemed such a strong connection. Additionally, I dropped phone number because that didn't seem all that relevant to whether someone stayed or goed. And then finally, I dummied the state, geographically where each account was, as well as the area codes. Sorry. Okay, so I then ran all of kind of the base models. So you can see here the table along the columns, the results, and along here are all the different models. And as you can see in red, they didn't perform as well. These likely overtrained because this was there was no testing. This is just kind of running basic. And then on the flip side, the gradient boost and XG boost did much better. You can see their training and test scores are better overall. And then more specifically, I focused on accuracy and recall. You can see those are both in kind of the blue boxes. And that overall, they better with these and focus on this because accuracy overall makes sense, I think, the general test. And recall because a false positive is much different here than a false negative. A false negative could be an issue with regards to, like, if we think a customer is going to leave and they stay versus customer stays and we think they're going to leave. And then going forward, I just assigned K&N to be the baseline model. And then this is just kind of a visual representation of this. Instead of doing a traditional matrix, just because there were so many models, I decided to put them all together. And so this is just kind of a heat map of all of the different models as well as the results. And this is on here is everything. And then on the left, you can see is just the testing results to zoom in kind of. So my first model I focused on was the gradient boost. And so after tuning, You can see on the top here are the recall and accuracy scores, because this is what I focused on. And as you can see in the red or orange bars are higher by 0.03 and 0.05. So not huge, but definitely something. But then also much higher than the baseline here. And then looking to the features themselves, as you can see with the graph here, this is the top 10. There were quite a few, but just looking at the most important ones. Customer service calls, the number of calls, the amount of their day charge, and whether or not they had an international plan seemed to be the most significant. Then moving on to the XGBoost. This was the second final model I ran, or tuned model. Similarly, the tuning improved it, but not by a lot. Similarly, you can see these are the red or orangey ones here. And they did a little better than the initial XGBoost models, but a lot better than the actual baselines. And then similarly, looking at the top features, you can see here, the top bars here are whether or not they had an international or a voicemail plan, as well as if they were based in Tennessee. So that was a binary dummy. But then also worth noting here is that none of these scores got over 0.1. You can see this here at the top is 0.8. I'm sorry, 0.08. So this should probably be taken with a grain of salt. And then just kind of the quick secondary note I decided to look at. Because this data is kind of the business model here is looking at whether customers stay or go, I decided to look at past customers. And so I analyzed the account length, right, how long they stayed. And then I looked at customers that had already left. And I assigned a dummy variable to see whether people were staying above average or below average. And not shockingly, there were still no real correlations. However, all of the correlations that stood out the most relatively were based on geography by location. These are all states, that's state category and the symbol. And then, for example, you can see here in this graph that, for example, everyone from Iowa, not a single one of them stayed above average. Like you can see here, everyone from the state of Iowa here, no one had an above average lifetime account. So kind of wrapping up, the top features that I found across all the models were the number of customer service calls, whether or not they had an international plan and whether or not they had a voicemail plan. These made it into the the top 5 features for both tuned models. And so given this, it's probably worth investing in a customer service and improving that because that's what's important to them, as well as targeting domestic customers because international plans seem to have a negative correlation, and potentially focusing on these 3 states. This was a rather small sample size, but it did show these to be the states where people stay the longest. And also just promoting their voicemail plan since that seemed to stand out the most. And then for possible next step, it would be useful to look at customers that did leave. As I mentioned, a fairly small percentage of the data I had that. And so I'm relying on kind of snowed data here, which hopefully is accurate. As well as finding other variables to analyze. As I mentioned, there were a few that were unimportant and a few that were just incredibly strongly correlated. So having more data about customers, potentially things like more demographic data, I think would be helpful. And then finally, just looking at kind of their competitors in the broader industry and seeing if these trends are common everywhere or if there's maybe something unique to this company. Thank you.
Awesome. Thanks, Sawyer. All right. So next should be Miriam, but she just messaged me saying that she has internet issues. So we're gonna move on to last but not least, Kishore. Oh, Kishore, you're still on mute.
Are you able to see my screen? Yeah. Okay. So I worked on the car crash data. This is basically like what I thought was like the and first initially I tried to predict the crash like for the future based on time. But since like the time series is going to be for the next project, I thought let me just do something else. So then I figured out after a few variations, I figured out like, okay, if it would be great if somebody can predict what kind of damages will cost them. So what I did is like I split it into two parts. One was like the damage cost, which will be more than $1,500, and the other one, which was less than $1,500. So that was the target variable which I worked on. So yeah, so the case was right, the cost which I wanted to work, and the database which I worked on was from the City of Chicago data website, and the data that was provided was between 2015 and 2020. Now, there are some interesting things that I found out while doing the exploratory data analysis. Right, one was like there were a lot of damages which were based on parked cars. So, right, so most of the times it seems like where people were turning and then they were like they found that they did the wrong turn and then they found that the cars were parked and then they crashed into it. And this is just one of my assumption worked on that. But otherwise, there were a lot of car crash, right? If we say, right, the speed of the car, which if it was beyond 65 and above, the car crashes were very high. That was one thing. And when it comes to the weather condition, one interesting thing I found was, if you see the number 10 here, it was basically like when there are severe storms, the crashes were to the minimum. So people probably did not move at all. That was my assumption based on that. But otherwise, like when there were windy, when there's special storms that were there, the damages were right on the higher side. The direction part, not much when people, right, when the cars were moving in different directions, there are not much of difference between whether you're moving in any direction. The car crash still happened. But then the cost of the crash has been increasing over the past 5 years. There is a steady increase that we can see. Now, the algorithm that I used was like after going through a lot of models, I shortlisted these 4 models: logistic regression, classification tree, naive-Bayes classifier, and KNN classifier. These were the models which after going through, because like for XGBoost and other things, like I found like it was taking too much time, and then I probably do not have the right kind of system. Maybe I'm just taking it for so maybe like I'll just work on that, increasing the database. Now, after running through all the models, I found that the most accurate or closest one was the logistic regression, because based on all the 3 parameters, whether it's accuracy, precision, or recall, which I ran, right? Logistic regression was the best, I felt. But then if you see the decision tree, right, was pretty close to the thing. So what I did was I ran both as 2 different notebooks. I tried both the models for the final part, and I've still I found that logistic regression was better in time. But I'm not sure once when I run through Yish for the review, then maybe we can figure out like why it was getting into that part. So that was my final model, which I used and then worked on. Next step, what I feel is like I would probably work on larger data set, right? And I want to predict crashes, which is based on time. Like if you are traveling on a particular location and on a particular time, right? How likely you're going to get into a crash situation, right? So that's all from me. This is my links. Anybody who's wanting to just check on. Thank you.
Awesome. Thanks, Kishore.